You pop out of a subway and breathe fresh air. You pull out your phone. The blue dot lands on your exact side of the street in seconds. How did it do that with no view of the sky? Here is the trick. That blue dot is not from one magic signal. It is a team job. Space clocks help. Cell towers help. Wi-Fi helps. Your phone's motion sensors help too. The app also draws a faint circle around the dot. That circle is the guess range. It is not a hard fence. First, clear up one myth. Satellites do not track you. Your phone only listens. It hears tiny radio whispers from space. It never talks back to the satellites. That makes the blue dot private to your device. Your phone can hear more than GPS. It also listens to GLONASS from Russia. It listens to Galileo from Europe. It listens to Beidou from China. More constellations mean more signals to use. Outdoors, a good phone can track 20 to 30 at once. More sky means better math and a faster lock. Those satellites ride high above you. They orbit at about 20,200 kilometers up. They loop the Earth about twice each day. Each one carries an atomic clock. That clock keeps time with crazy stability. Your phone needs that time to figure out distance. Here is the core idea. Time is location. Each satellite sends a timestamp. The signal races at the speed of light. If your phone sees a tiny time delay, that becomes distance. 1 nanosecond off means about 30 centimeters of error. Your phone solves for X, Y, and Z. It also solves for its own clock error. That is why it needs at least 4 satellites for a 3D fix. Physics even sneaks in relativity. Clocks in orbit tick a bit faster than clocks on Earth. The net difference is about 38 microseconds per day. The GPS system pre-corrects the clocks. If it did not, your blue dot would drift around 10 kilometers every day. That is a wild miss for a coffee run. A quick history pit stop. The first GPS satellite launched in 1978. Full service went live in 1995. For years, the signal for the public was blurred on purpose. In May 2000, that blur was turned off. Accuracy jumped from near 100 meters to about 10 to 20 meters overnight. The world changed for maps that day. Now listen to the whisper itself. The main GPS signal most phones use is called L1. It sits around 1575 megahertz. Many newer phones also use L5, around 1176 megahertz. L5 helps fight bad reflections in cities. The power at the ground is tiny. Think about 1/10 quadrillionth of a watt. That is below the noise around you. So how do we hear it? The trick is a known pattern in the signal. It is a 1 millisecond code that repeats. Your phone lines up a matching pattern and slides it back and forth. When the peaks line up, the phone locks on. That process is called correlation. The data inside crawls in at about 50 bits per second. Slow, but steady. Satellites send 2 kinds of orbit hints. The almanac is a rough guide for where every satellite will be. It stays useful for weeks. The ephemeris is the precise track for one satellite. It stays fresh for only a few hours. If your phone has nothing cached, it must pull this over the air. That can take time. That is why you hear about cold and hot starts. A true cold start can take half a minute to a minute to get a fix. A warm start is faster. A hot start with fresh ephemeris can lock in a few seconds. Phones also use assisted GPS. Since around 2008, they grab time and orbits over the internet. That can cut time to first fix to under 5 seconds. You feel this on a trail versus a city. Power off your phone all night on a remote hike. In the morning, the fix takes a while. In a city with data, the same phone snaps to your spot fast. It already knows who is in the sky and where to look. But what about indoors or under concrete? Cell towers help first. Your phone knows which tower you are near. That gives a rough area. It can be a few hundred meters in a dense city. It can be a few kilometers in the countryside. It is not precise, but it is instant. Wi-Fi adds a sharper picture. Big databases know where many routers live. Your phone can guess a building from that. On some gear, Wi-Fi can do round-trip time. It pings a router and measures the bounce time. That gives distance within about 1 to 2 meters when the setup is good. Height is its own puzzle. Your phone has a tiny barometer. Air pressure drops with height. With weather data to calibrate it, the phone can nail your floor within 1 to 3 meters. That helps rescuers and elevators. It also helps that blue dot feel right in a mall. Your phone also watches your motion. The accelerometer feels steps. The gyro tracks turns. Short term, it can dead reckon your path for a few seconds. That smooths the dot while the radio math catches up. It also helps when the sky view comes and goes. The map itself joins the job. The system knows where roads and doors are. It snaps your path onto likely lines. This is called map matching. It fixes wobbles. It can also be too confident and put you on the wrong parallel road. So the system keeps a measure of doubt. That faint blue circle is that measure. It comes from the fused estimate and its confidence. Often, it is about a 1 sigma radius. In plain words, the phone is saying, I am probably inside this circle. If the data gets worse, the circle grows. If it gets better, it shrinks. Cities throw a special curveball. Tall glass towers bounce signals like mirrors. That ghost path is called multipath. It can shift your dot by tens of meters. Dual frequency helps here. L5 lets the phone spot bad bounces and trust cleaner lines. In good spots, that tightens accuracy to around 1 to 2 meters. Phones and map providers now push even harder. Google rolled out 3D building corrections on Android. The system uses city models to bias the fix away from likely reflections. In midtown tests, blue dots that jumped across the street came back to the right side. Errors of 20 to 50 meters dropped to single digits. All of this could eat your battery. So the system is careful. The satellite chip can sip only tens of milliwatts when used in short bursts. The phone wakes it, grabs fresh data, then lets it nap. Between bursts, sensors and Wi-Fi carry the path. There is a brain that blends it all. On Android and iOS, a fused location provider mixes satellites, Wi-Fi, Bluetooth, barometer, and motion. It shifts the weights on the fly. In a park, satellites lead. In a dense block, the system may downweight GPS and lean on sensors and Wi-Fi more. Your dot stays calm. Sometimes things still go weird. Stale ephemeris slows you down. Deep valleys block the sky. Inside planes, the metal shell is rough on signals. Jammers can also cause chaos. In 2019, some older devices broke when the GPS week number rolled over. Time formats matter more than you think. Help still gets through when it counts. During a 911 or 112 call, phones blend every tool. Satellites, Wi-Fi, cell, barometer, and motion all join. Dispatch can get a floor level in many cities. Rules in the United States push for about plus or minus 3 meters in height. That saves minutes when minutes count. So what is next for your blue dot? More phones speak L5 and Galileo now. City-scale 3D fixes keep improving. Since 2016, Android has let apps read raw satellite data. That has opened research for centimeter tricks like RTK and PPP in good sky. Indoors, new radios help too. Ultra-wideband can measure distance to under 30 centimeters in places that support it. It is not everywhere yet. Real accuracy still depends on sky view, phone design, and software. But the arrow points the right way. Here is the part I love. Every time you tap center, a hidden orchestra starts. Space clocks tick. Light speed math runs. Wi-Fi pings. Air pressure shifts. A city model pushes back on reflections. All so casual, you never notice the physics showing off. Thanks for hanging out. See you next time.